Okay, so let's jump right into this paper. Vision transformers need registers. It's pretty interesting. It takes a look at how vision transformers work, VITs, and finds some unexpected things going on in these models. We're talking about these high norm tokens, which kind of pop up in weird places and act a little strangely, like finding a spike in your data when you'd expect a smooth curve. So the researchers look mostly at Dino V2, a self-supervised VIT model, but they saw this in other VITs too, like D3 and OpenSlip. So today we're going to break down what these artifacts are, why they matter, and what these guys propose we do about it.
Yeah, what's really interesting here is that these high norm tokens are essentially vectors with unusually high magnitudes, and they show up in the middle layers of these big, well-trained VITs, and they tend to cluster in areas of the image that look similar, like a plain background.
So they're not just like randomly scattered all over the model. It seems
Okay.
like they prefer certain types of image content.
Exactly. And that's, one of the things that got these researchers thinking. They wanted to understand why these high norm tokens were showing up in these specific spots and what they were doing in the model as a whole.
Now, you mentioned that these high norm tokens are basically vectors. Can you explain that a bit more for our listeners? How do vectors relate to the way VITs process images?
Sure. So VITs take an image and break it down into these smaller patches. Each patch becomes a vector or a token. These tokens then go through the transformer network, which learns to pull out features and relationships between them. You can think of it like each token is a puzzle piece, and the transformer is trying to figure out how all the pieces fit together to make the whole picture.
Okay, that's a helpful way to look at it. So these high norm tokens, are they like special pieces that the model is using differently?
Yeah, that's a good way to think about it. What they found was that these high norm tokens, even though they really stand out, weren't actually carrying much local information about their specific patch or where they were in the image. They were kind of losing touch with their original puzzle piece.
So if they're not representing their patch, what are they doing?
Well, that's where it gets really interesting. They did a bunch of clever experiments to see what kind of information these high norm tokens were actually encoding. One thing they did was train a simple linear model to predict the position of each token in the image. What they found was that models trained on these high norm tokens were terrible at this compared to models trained on regular tokens.
So that kind of supports the idea that these high norm tokens are losing their spatial awareness.
Yeah, exactly. They also trained another linear model this time to rebuild the original image patch from the token representation. And again, models using these high norm tokens did a really bad job at recreating the local image details compared to the ones using regular tokens.
So these high norm tokens are definitely ditching the local spatial information in favor of something else. But the question is, what are they encoding instead?
So to figure that out, they did a third experiment, this one focusing on image classification. They took the token representations from the model and trained a simple classifier to predict what category the image belonged to. And here's the crazy part. Models trained on these high norm tokens did surprisingly well at this classification task, even better than the ones trained on regular tokens in some cases.
Wow. So even though these high norm tokens are losing their local information, they're actually picking up valuable global information about the image. So they can still help with big picture tasks like classification.
Exactly. That's what led them to this idea of the tokens acting like registers. They think the model is basically finding tokens that aren't that important for representing local details and then using them to store and process global information instead.
It's like the model's getting smart and figuring out how to optimize its internal workings, using certain tokens as its own little scratch pad.
Right. And they don't think this is necessarily a bad thing. It might even be a sign that the model is getting smarter, figuring out efficient ways to represent information. The problem is when this register behavior starts messing with tasks that need very precise local information.
Right. Like if you're trying to solve a puzzle, and instead of using all the pieces the right way, you start using some pieces as notepaper to write down your calculations. It might help you solve the puzzle, but those pieces aren't showing they're part of the image anymore. So how did the researchers say we should fix this?
Their solution is actually pretty simple but elegant, dedicated register tokens. Basically, they say we should add a few extra tokens to the VIT sequence, but separate from the image patches, like giving the model a proper notepad instead of having it scribble notes on the puzzle pieces.
So it's like giving the model a proper place to do its work instead of having it mess up the puzzle pieces. Did they try this out, and what happened?
Yeah, they did, and the results are really impressive. Adding these dedicated register tokens gets rid of those high norm token artifacts. The distribution of token norms evens out and becomes much smoother. This means that the patch tokens can go back to focusing on representing their parts of the image.
That's great. So giving the model a designated space for its global computations stops it from needing to use those patch tokens as makeshift registers. But did this only affect the artifacts, or did it change how well the model performed overall?
That's where things get really interesting. Not only did adding register tokens get rid of the artifacts, but it also made the models better at a bunch of different tasks, like image classification, object detection, and even semantic segmentation.
So it wasn't just a quick fix. It actually made the models better at what they do.
Exactly. And the fact that this small change can have such a big impact really shows how well these researchers understand how these models learn and process information.
Now, I'm curious about how they actually figured out these artifacts were there. How did they measure and quantify the presence of these high-norm tokens?
They used something called token norm. It basically measures how strong or prominent a token is in the model's internal representation. They found that in models with this artifact, the distribution of token norms wasn't smooth. It had this weird shape with two peaks.
Two peaks. What does that mean?
It's called a bimodal distribution. Imagine a chart showing the heights of people in a group. If you have a bunch of people who are much taller than everyone else, you'd see two peaks on the chart, one for the average height and another for the taller group. It's the same idea with the token norms. They saw one peak for most of the tokens with regular norms and another peak for a smaller group of tokens with really high norms. Those were the outliers.
Okay, so this weird two-peaked distribution of token norms was a clear sign that something strange was happening in the model, with certain tokens standing out from the rest. And they specifically looked at tokens in the middle layers of the network, right?
Sure.
Why was that?
Yeah, they noticed that these high-norm tokens didn't show up right away in the early layers. They tended to pop up and become more obvious in the middle layers, which suggests that the way the model was processing information was changing as data moved through the network.
So it's like the model is first focusing on getting the local features from the image patches. And then as it goes deeper, it starts to use some tokens for these bigger global calculations, which is when those high norm tokens appear.
You got it. Their analysis definitely showed a progression in how the tokens were behaving as information flowed through the network. And to really make sure their hunch about these high norm tokens acting as registers was right, they came up with some really clever experiments.
Oh, interesting. Tell me more about those experiments.
They designed these experiments to figure out what these high norm tokens were actually learning. The idea was to see what information these tokens held and how it was different from regular tokens. One of their main experiments was something we talked about earlier, linear probing.
Right, where they trained a simple linear model using the token representations to see what kind of information those tokens were holding.
Exactly. They use linear probing for a few different things. First, they try to predict where each token was in the image. They found that linear models trained on these high-norm tokens were much worse at this than models trained on regular tokens.
So that gave them more evidence that these high-norm tokens were losing their connection to their original spot in the image and were instead encoding something more about the whole picture.
Exactly. Then they tried another thing. They trained another linear model to try and rebuild the original image patch from the token representations. And again, models trained on the high-norm tokens did a much worse job at recreating the local details of the image compared to the models using regular tokens.
Okay, so that's two things pointing to the same conclusion. These high-norm tokens are getting rid of local spatial information. But what are they encoding instead?
To answer that question, they did another linear probing experiment, but this time they focused on image classification. They trained a linear model on the token representations to see if it could predict what category the image belonged to, and what they found was pretty amazing.
What did they find?
The models trained on these high-norm tokens were surprisingly good at the image classification task. They even beat the models trained on regular tokens sometimes.
So even though these high-norm tokens weren't good at remembering where they were or what their original patch looked like, they were really good at image classification. This means they must have been holding on to some important global information that helped them understand the whole image.
Precisely. And this finding really solidified their idea about these tokens acting as registers for global information.
Okay, so we've established that these high-norm tokens are popping up in these models, and they're repurposing themselves to encode global information. But how does this connect to the solution they're proposing with the dedicated register tokens?
That's a great question, and we'll get into that next.
So we've spent a lot of time talking about these high-norm tokens, how they behave, and how they seem to work as like these makeshift registers for global information. But the paper doesn't stop there. It actually proposes a solution. These dedicated register tokens. It's a pretty neat way to solve the problem, but I'm wondering how they got to this idea. Did they just stumble upon it, or was there like a process that led them there?
That's a really good question, and it highlights something important about research. It's all about this back and forth of seeing something, coming up with an idea, testing it out, and then refining it. These researchers didn't just jump to this idea of dedicated registered tokens. They got there through a bunch of carefully designed experiments and analyses.
It's like a detective solving a case following the clues to find the truth.
Exactly. They started by noticing this weird behavior of high-norm tokens. They saw these tokens showing up in specific patterns, mainly in the middle layers of the network, and they realized that these tokens were getting worse at representing local information, but surprisingly better at encoding global information.
Right, we talked about those linear probing experiments where the high norm tokens were terrible at figuring out their location or rebuilding their original patch. But they were great at image classification.
Exactly. Those findings were super important for guiding their thinking. They realized that the model was basically trying to find a way to represent global information, but it was doing it in a messy way by kind of hijacking these patch tokens.
So it's like the model was trying to solve a problem but didn't have the right tools. So it improvised and repurposed some of its existing parts.
Exactly. And that's when they had this aha moment. They realized that if the model was already trying to create these registers, why not just give it dedicated tokens that are specifically designed for that?
It's like giving the model a proper hammer instead of forcing it to use a rock.
Right, exactly. And that's how they came up with the idea of dedicated register tokens. They figured that by giving the model these special spots to store global information, they could let the patch tokens go back to doing what they were supposed to do, representing the image accurately.
Okay, so that's the thinking behind the idea. But how did they actually make these dedicated register tokens work? Did they just stick them at the beginning of the token sequence, like a class token?
Well, they tried putting these register tokens in different places, and it turns out that the exact spot in the token sequence didn't really matter much.
So they tried putting them at the beginning, in the middle, and even at the end.
Exactly. And no matter where they put them, the model was able to use them just fine.
Interesting. So it seems like the model is flexible enough to use these dedicated registers no matter where they are in the sequence.
Exactly. Now, another thing they had to figure out was how to initialize these register tokens. They tried a few different things, like starting them with random values or with the average value of all the patch tokens.
So they were trying different ways to give these register tokens a starting point before the model started learning.
Right. And what they found was that while the initialization did affect things early on in the training process, it didn't really matter much for the final performance of the model. Basically, the register tokens figured out how to represent the global information they needed, regardless of how they started.
It seems like the model is smart enough to learn what these registered tokens are for and how to use them no matter what their starting values are. Which makes sense if the model is actively learning to use these tokens for their intended purpose.
Mm-hmm.
Now, you mentioned earlier that they experimented with different numbers of these register tokens. Did they find that more is always better?
That's a good question, and it turns out it's not that simple. They did some experiments to see how the number of register tokens affected performance, and it wasn't as straightforward as you might think.
Oh, that's interesting. What did they find?
They found that adding just one or a few register tokens usually gave the biggest improvement in performance. But adding more than that didn't always help, and sometimes even made things a little worse.
So there's like a sweet spot, a point where adding more register tokens doesn't really help anymore.
Exactly. Too few, and the model doesn't have enough space to store all the important global information. Too many, and things can get too complicated, or the model might start overfitting, which means it gets too good at remembering the training data, but doesn't work as well on new data.
Right. Overfitting is always a problem in machine learning. It's like studying too hard for a test and just memorizing the answers instead of understanding the material. Then you're lost when you see new questions.
Exactly, and that's why finding the right balance is important. The researchers think that the best number of register tokens depends on things like how complex the task is, how big the model is, and what the data is like.
So there's no one-size-fits-all solution. You need to figure out the best number of register tokens for each specific problem.
Right, and that's why experimenting and testing things out is so important in machine learning research. It's not always about finding a single perfect solution that works everywhere. It's about figuring out the best approach for each situation.
Now I'm curious about how these register tokens relate to the idea of memory in machine learning. I know memory is a big deal in AI these days with models like ChatGPT that can store and remember tons of information. Do these register tokens act like a kind of memory for the model?
That's a really interesting question. And it connects this research to other areas of AI. The researchers actually compare their register tokens to something called memory tokens that have been used in natural language processing.
Oh, interesting. Can you tell me more about that?
Sure. In natural language processing, people have been working on models that can store and retrieve information from a separate memory bank. These memory tokens act like pointers to specific pieces of information, which lets the model access relevant context even when it's processing long sequences of text.
So it's like giving the model a library it can use while it's reading a book, helping it understand the story better by giving it more context.
Exactly. And the researchers in this paper think that their register tokens are doing something similar in vision transformers. They're giving the model a special place to store and access global information that might be important for understanding the whole image.
So basically, these register tokens are acting like a kind of global memory for the model, letting it keep track of the big picture, even while it's processing individual parts of the image.
Exactly. And this connection to memory is a really cool area for future research. Could we design models that can choose what information to store and retrieve from these register tokens? This could lead to even more advanced reasoning and decision-making.
That's a fascinating idea. It opens up so many possibilities for what these models might be able to do. Seems like we've covered a lot about these dedicated register tokens, how they work, and the benefits they bring. What are your thoughts on how these register tokens affect things visually? Like you mentioned earlier that they make the attention maps look better. Can you tell me more about that?
Absolutely. Attention maps are a really cool way to see what parts of an image a model is focusing on when it's making its predictions. They're like heat maps that show the most important regions of the image.
Right. It's like seeing where the model is looking when it's looking at an image.
Exactly. And in models without these dedicated register tokens, the attention maps often look kind of weird and messy, especially in those areas where the high norm tokens were. It was like the model's attention was being pulled in too many directions, creating a lot of visual clutter.
Okay, so the attention maps were hard to understand.
Right. But when they added the register tokens, something amazing happened. The weird patterns in the attention maps went away, and the maps became much smoother and easier to follow. It was like the model could finally focus its attention better, highlighting the really important parts of the image.
So it's like those register tokens help to declutter the attention maps, making it easier to see what the model is really paying attention to.
Exactly. And this improvement in attention maps actually made a difference in tasks like object detection and semantic segmentation, where paying attention to the right things is really important. The models with dedicated register tokens were better at doing these tasks because their attention wasn't being distracted by those high norm tokens trying to act as registers.
That makes sense. If the model can focus better, it's going to be better at finding and understanding objects in an image. Now, another interesting thing about these register tokens that we talked about earlier is that they can specialize. The researchers noticed that these tokens weren't just acting as a big pool of global information, they were actually developing specific roles during training. Can you tell me more about that?
Of course. This part of their research shows how incredible these models are at learning. They found that during training, certain register tokens would start to prefer certain types of information. For example, some tokens would always focus on the background of the image, while others might focus on the objects in the foreground.
So it's like the model was automatically dividing up the work among the register tokens, with each token becoming an expert in a specific part of the image.
Exactly. And this specialization wasn't something they programmed into the model. It happened naturally as the model learned how to best use these register tokens.
That's amazing.
Hmm.
It's like watching the model evolve and figure out the most efficient way to use these new tools it has.
It really is. And this opens up some really cool questions for future research. Can we understand this specialization process better? Can we guide it to create even more specialized and efficient representations?
Those are great questions. It seems like we're just starting to understand what these register tokens can do.
I completely agree. This research is really just the beginning of a much bigger exploration of how we can make transformer models even better and unlock their full potential.
Now, before we move on, I want to talk about something you mentioned earlier, the potential downsides of using register tokens. They seem to have a lot of benefits,
Yeah.
but I imagine there are also some things to be careful about. Can you tell me more about that?
You're right. Like, with anything you change in machine learning, there's always a trade-off. One thing to watch out for with register tokens is that they can make things more computationally complex.
Right, adding more parts to the model means more calculations, which could make it slower.
Exactly. Adding register tokens means the model has to process more things each time it runs, which could slow down both training and inference times.
So if you're working with a really big model, or if you don't have a lot of computing power, that extra computational cost is something to think about.
Precisely. Another potential issue is the risk of overfitting, which we talked about earlier. This happens when a model gets too good at remembering the training data, but doesn't generalize well to new data. Adding more things for the model to learn, like register tokens, can make this problem worse.
Right, because with more things to learn, the model can get more specific to the training data
Yeah.
and might not work as well on new data.
Exactly. So it's important to be aware of these potential downsides and try to minimize them. Luckily, a lot of the techniques we already use to prevent overfitting in deep learning, like dropout and weight decay, can also be used with register tokens.
Okay, so it sounds like there are ways to manage these risks. But overall, it seems like the benefits of register tokens outweigh the potential problems.
I agree. The improvements in performance, attention map quality, and how easy it is to understand the model are pretty convincing evidence that this approach is worth it.
Now, I want to switch gears a bit and talk about how this research might influence what happens next in the field of vision transformers and AI in general. This paper is mostly focused on things we do with images, but do you think what we've learned about register tokens and global information processing can be applied to other areas of AI too?
That's a fantastic question, and I think the answer is definitely yes. Transformers are a very versatile architecture that has worked really well in lots of different areas, from natural language processing to audio analysis to even robotics.
Right, we've seen some amazing breakthroughs lately with models like ChatGPT and DALL-E, which all use the transformer architecture.
Exactly. And the main idea from this research about explicitly adding ways to handle global information in the transformer architecture could be used in all sorts of applications.
So it's not just about images. It's about any task where the model needs to understand the big picture while also processing the individual parts.
Exactly. For example, imagine a language model that's trying to understand a really long and complicated legal document.
A task where understanding the main points and arguments is super important.
Exactly. In this case, you could add dedicated register tokens that learn to represent the key concepts or themes in the document.
So as the model is reading each sentence and paragraph, it can also check these register tokens to keep track of the overall meaning.
Precisely. These register tokens would be like a global memory helping the model make better predictions about what the text means. And you could use a similar approach in other areas too.
So in audio processing, you could have register tokens that represent different musical instruments or different people talking. And then in robotics, you could have register tokens that represent the overall goals of a task or the state of the environment. There are so many possibilities.
Absolutely. And that's what's so exciting about this research. It's not just about fixing a specific problem in vision transformers.
Yeah.
It's about finding new ways to make these models even better and unlock their full potential in all kinds of applications.
Now, before we finish up this part of our deep dive, I want to go back to the idea of object discovery, which seems to benefit a lot from using register tokens.
You're right. Object discovery is a really interesting and challenging task in computer vision. It's about finding and locating objects in an image without having any labels or annotations.
So it's like the model is trying to figure out what's in an image without being told what to look for.
Exactly. And this relies on the model being able to learn good representations of the visual world.
And like we talked about before, those high-norm tokens acting as makeshift registers were messing things up for object discovery methods because they were adding noise and making the attention maps inconsistent.
Exactly. Those artifacts were making it hard for the model to accurately separate and identify objects. But by adding dedicated register tokens, we get rid of those artifacts, which gives us much clearer and more understandable attention maps.
And with better attention maps, object discovery becomes much more effective.
Exactly. The researchers tested this out by seeing how their models performed on object discovery benchmarks, and they saw a big improvement in performance. The models with register tokens were much better at finding and locating objects in the images.
That's a really strong sign that fixing these little architectural quirks can actually make a big difference. It's not just about making things look nice on paper, it actually makes these computer vision tasks work better in the real world.
Absolutely. And it suggests that this research could lead to big advances in areas like robotics and self-driving cars, where being able to detect objects accurately is super important.
I totally agree. The things we've learned from this research can help us design and train better vision transformer models in the future, which will lead to systems that are even more powerful, reliable, and robust.
I couldn't agree more. This deep dive has been incredibly insightful, and I feel like we've just scratched the surface of this fascinating topic. What are your thoughts on the bigger picture significance of this research, and what are some key takeaways for our listeners? It's been great diving into this paper with you. Finding these high norm token artifacts and coming up with the solution of dedicated register tokens is a big step forward in how we understand and optimize vision transformer models.
Okay, so let's summarize some of the key things we've learned. First, we learned that these high-norm tokens, which act like makeshift registers for global information, are something that happens a lot in vision transformers.
Exactly. And second, we discovered that while this behavior might be good for some tasks, it can also make it harder for the model to do things that need really precise local information, like object discovery.
All right, it's all about finding the right balance between global and local information processing.
Exactly. And third, we learned that adding dedicated register tokens is a simple but elegant way to fix this problem, which leads to better performance on a lot of different tasks.
It really shows how important careful observation, thoughtful experimentation, and creative thinking are in machine learning research.
Absolutely. And I think this research has the potential to change the future of computer vision and AI in general. It gives us new ways to think about how to improve transformer architectures so they can process and understand complex information even better.
This deep dive has been really insightful, and I'm sure our listeners have a much better understanding of how vision transformers work now. Stay tuned for the last part of our discussion where we'll wrap up our exploration of this fascinating topic. All right, so welcome back to the last part of our deep dive into vision transformers. We've been talking about this really interesting paper, Vision Transformers Need Registers. And I feel like we've covered a lot of ground exploring these high-norm token artifacts and the whole idea of dedicated register tokens.
It's been a great journey for sure. We've really dug into the technical stuff, the experiments, the results, and what it all means. But I think it's good to step back for a minute and think about the bigger picture. What does this research tell us about AI, where it's going, and the challenges and opportunities we have ahead?
Yeah, that's a good point. It's easy to get lost in all the details. But what really matters is what this research means for the future of AI and how it can change the world.
Absolutely. And I think one of the most important things we can take away from this research is that we're still just scratching the surface of understanding how these powerful AI models really work.
Right, we've come a long way, but there's still so much we don't know about how these models learn, represent information, and make decisions.
Exactly. And this research is a perfect example. We've been using vision transformers for a while now, and they've been doing really well on different tasks. But it turns out there's all this stuff going on under the hood that we're just starting to figure out.
It's like we've built these incredible machines, but we're still trying to figure out how all the parts fit together.
That's a great way to put it. And that's why research like this is so important. It helps us peel back the layers and understand these models better. And the more we understand them, the better we can make them more efficient, more robust, and more reliable.
Now, you mentioned before that this research shows how adaptable vision transformers are, how they can use things like tokens for jobs they weren't designed for. Do you think this adaptability is a good thing or a bad thing?
That's a tough one. I think it's both. On one hand, it's amazing how flexible and powerful the transformer architecture is. It can learn and adapt in ways we never expected.
It's like the model is smart enough to figure out how to solve problems in creative ways.
Exactly. But this adaptability can also lead to unexpected things happening, like those high-norm token artifacts. And sometimes those unexpected things can cause problems, as we saw with object discovery.
So it's kind of a double-edged sword. We want models that are flexible, but we also need to understand and control that flexibility so they're used in the right way and don't cause any harm.
Exactly. And I think that's one of the big challenges for AI research going forward. Finding that balance between flexibility and control, letting these models learn and explore, but also making sure they're doing what we want them to do.
It's like raising a child. You want them to be curious and creative, but you also need to set boundaries and guide them so they grow up to be responsible and well-rounded.
Perfect analogy. It shows how important it is to not just build bigger and more complex models, but also to do research that helps us understand how they work, how they learn, and how to interact with them effectively.
Now, this research mostly focuses on image-based tasks.
Yeah.
But you mentioned earlier that what we're learning about registered tokens and global information processing could be used in other areas of AI too. Could you give us some specific examples of how these ideas might be applied in other fields?
Absolutely. Like we've talked about, transformers are a really versatile architecture that has been successful in a lot of different areas, like natural language processing, audio analysis, and robotics.
We've seen them used for all sorts of things.
Exactly. And this main idea from the research about adding special mechanisms to handle global information in the transformer architecture could be used in all of those areas.
So it's not just about images. It's about any task where the model needs to understand the big picture, while also processing the individual pieces.
Exactly.
Yeah.
For example, let's say you have a language model that's trying to understand a really long and complicated legal document.
Right, where understanding the main points and arguments is crucial.
Exactly. In that situation, you could add dedicated register tokens that are trained to represent the key concepts or themes in the document.
So as the model is reading each sentence and paragraph, it can also check these register tokens to keep track of the overall meaning.
Exactly. Those register tokens would act as a global memory, helping the model understand the text better. And you could use a similar approach in other areas, too.
So you could have register tokens that represent different musical instruments or speakers in audio processing. And in robotics, you could have them represent the goals of a task or the state of the environment. It seems like there are so many possibilities.
There really are, and that's what's so exciting about this research. It's not just about fixing a specific problem in vision transformers. It's about opening up new ways to think about how we can make these models even better and use them for all sorts of things.
Now, before we wrap up this whole deep dive, I want to go back to something you said earlier about how it's important to not just focus on making bigger and more complex models, but also to do research that helps us understand how these models work.
Yeah.
Why is that so important, and what are some of the challenges?
That's a really important point. It's easy to get caught up in the excitement of building bigger and better models, but we also need to understand what's going on inside them, how they're making decisions, and what the consequences of those decisions might be.
It's not just about getting the best performance. It's about making sure these models are trustworthy, transparent, and aligned with our values.
Exactly. And one of the biggest challenges in understanding these models is how complex they are. We're talking about systems with billions or even trillions of parameters, and the way they interact is incredibly intricate and often hard to understand.
It's like trying to understand how a giant machine works with all these interconnected gears and levers.
Exactly. And the traditional ways we analyze these models, like looking at the weights or activations of individual neurons, don't always tell us the whole story.
Yeah.
We need to develop new tools and techniques that can help us unravel this complexity and really understand how these models learn and make decisions.
So it's not just about building better models. It's about building better tools to understand those models.
Exactly. And I think that's going to be a big focus of AI research in the future. We need methods that can help us visualize and interpret what's going on inside these models, to find potential biases and vulnerabilities, and to make sure they're making decisions in ways that are aligned with our values and goals.
Like we're explorers going into uncharted territory. We have these powerful ships that can take us there, but we also need maps and compasses to help us navigate safely and effectively.
I love that analogy. It really captures the spirit of this research. We're on a journey of discovery, and it's not just about reaching the destination. It's about understanding the journey itself, the challenges we face, the opportunities we find, and the lessons we learn that will help us create a future where AI can truly benefit humanity.
This deep dive has been a fantastic exploration of one small but important step on that journey. We've really dug into the details of vision transformers, found some unexpected things, and explored solutions that can shape the future of AI. It's been inspiring to see how far we've come, but also humbling to realize how much more there is to learn.
I feel the same way. And I believe that if we stay curious, keep working together, and stay committed to ethical and responsible development, we can navigate this uncharted territory and create a future where AI helps us solve some of the world's biggest problems.
Thank you so much for joining me on this deep dive. It's been a really insightful conversation. And of all our listeners out there, we hope you've enjoyed this journey as much as we have. Stay curious, keep exploring, and join us next time as we dive into another exciting part of the AI world.